Hello everyone. We're going to go over section 3.2 today, product and quotient rules. We're actually going to do this in two parts. Today I'm just going to go over the product rule, and then the next day I'm going to go over the quotient rule. Okay, so from the day previous, we looked at the sum and difference rule, and that is if you have y equals to some f of x plus some g of x, or subtract g of x, then the derivative would be the sum of the derivatives individually, or the difference of the derivatives individually. Now, is that still true for any product or any quotient? It turns out to be not the case. So this is a big no here. If we have y equals f of x times g of x, the derivative y prime would not be f prime of x times g prime of x. Likewise, if we have a quotient of y equals f of x over g of x, its derivative y prime will not be f prime of x over g of x. So these are both incorrect. So we're going to prove this by a counterexample. From yesterday, you saw that we are able to take derivative of the product of polynomials simply by multiplying them together. So what we can do for example A is to multiply 3x squared and 4x together to get 12x cubed. And then of course, we can then take the derivative, and that will be 36x squared. If we were to try to apply this incorrect rule and take the derivative of each individual piece and simply multiply them together, the derivative of 3x squared will be 6x, and the derivative of 4x will be 4, and you actually get 24x, which of course we know is incorrect. Likewise, if we were to divide on the right hand side, for example B, we can divide first. 6 divided by 2 is 3, and then the quotient of the powers here will be just x squared. And of course, then the derivative will be 6 times x. Okay, so if we were to take the derivative using the incorrect method, then y prime would be equal to 30x to the fourth power divided by 6x squared. And if you divide that, you will actually get 5x squared, which again is not 6x. So we know for a fact that this is incorrect. So what is then the correct product rule for derivatives? If we're given y equals f of x g of x, and then the derivative, y prime, is actually going to be f prime of x g of x plus f of x g prime of x. We're not going to go over the proof here for now. It might be a homework question or um, something like that. So I'm going to leave that for homework. But um, it does work, and we're going to show that by redoing one of the previous examples just to demonstrate. There was an interesting question in class today as well about what happens if we have more than two functions being multiplied together. So I'm going to demonstrate that to the side here. So let's say we have y is equal to f of x, g of x, h of x. And then if we were to take its derivative, we will follow the rule that we have here. So y prime will be equal to f prime of x. And then, of course, we leave the rest of the function alone. We can treat g of x and h of x as though they're um, like its own function. So something like this. And then for the second piece, we're going to leave f of x as is and take the derivative of g of x, h of x. And we will denote that using a little dash mark here. So if we were to go ahead and expand that, then we will simply apply the product rule again. We'll get rid of the parentheses here for g of x, h of x. We don't need those anymore. So the derivative of g of x h of x multiplied together would be g prime of x h of x plus g of x h prime of x. So again, applying the product rule, kind of nested within its own question. And then finally, you can multiply everything out. So you'll get y prime is equal to f prime of x, g of x, h of x, plus f of x, g prime of x, h of x. And finally, when you use the distributive property, you'll get f of x, g of x, and then h prime of x. Okay, so it's kind of like an expansion on the original product rule, and that is you take the derivative of the f of x, and then you take the derivative of the g of x, and then you take the derivative of the h of x, and you simply multiply everything together, and then you add each one of these three components together to get your derivative. So a little bit more involved for sure, but um, I figure I'll share the um, solution because somebody was asking today during class. Okay, so going back to applying the rule to our previous example, if we were to find this is y equals, then y prime, we'll take the derivative of 3x squared, which is of course 6x, and then we have 4x, we just leave g of x as is for now. Again, if you like, you should definitely label which function is f and which function is g. And then we're going to add 3x squared, right? You don't take the derivative of f again. And then we take the derivative of g of x, which is just 4. We can then multiply everything out. 6 times 4 is 24. And then we have x squared. And then 3 times 4 is 12. And also x squared. So if you add them together, you will get 36x squared, which is what we had um, before when we multiply everything together first. Um, can I undo that? Yes. Okay, good. So now you will notice that for these questions, you can actually just multiply things together and then take the derivative. So it doesn't necessarily make a lot of sense to use the product rule. The product rule is more useful when you have different kinds of function combined together as a product. So let's say you have a 2 to the x power times x squared, something like this. So let's say you have y equals, um, I don't know, x cubed times 2 to the x. Then you cannot simply multiply these two together, and that's when you're going to use the product rule. Okay. So let's go over a couple more examples just to demonstrate the rule again. So a couple more. So first one here, we're going to go ahead and rewrite the terms. It's always a good idea. Makes life easier for us. So we're going to write this as y equals, and then x to the 2/3 power, and then 2x minus x squared. Now, from there, we can apply the product rule. The derivative of x to the 2/3 power, of course, will be 2/3, and then x to the negative 1/3 power. 2/3 minus 1 is negative 1/3. And then, of course, we're going to leave the second part as is. And then we're going to leave the first part, and then the derivative of the function g of x, which is in the parentheses here. Derivative of 2x is 2, and derivative of x squared is, of course, 2x. Then what you can do is multiply everything out using the distributive property. So 2/3 times 2 is 4/3. X to the negative 1/3 plus 1, that will give you 2/3. And then continuing the distributive property, you have 2/3. And then, of course, negative 1/3 plus 2 is going to be, that will be 6/3. Okay, so that will be 5/3. just adding fractions here, which oddly enough is the where a lot of mistakes kind of come from when people do this kind of question. So next part, 2, and then x to the 2/3, of course, simply multiply by 2. And then, of course, x to the 2/3 multiplied by 2x, you'll get 2x to the 5/3. So what you notice here is that the first and third term are both x to the 2/3 power, and likewise the second and fourth terms are both x to the 5/3 power. So you can actually treat them as like terms and simply um, add them together. So then we have y prime is equal to see 10/3 x to the 2/3, and then minus 8/3 x to the 5/3. Now, from there, what you're going to do, of course, is rewrite this with uh, square roots, if at all possible. So this would be 10, and then the cube root of x squared all over 3 minus 8, and then the cube root of x to the 5th power also over 3. Now, in some textbooks, they will not write the term like this. They will actually rewrite it as x times x to the 2/3, right? And then they will write this as x and then the cube root of x squared. So that's a possibility as well. Okay. But either way, so long as you took the derivative and your um, exponents are correct, then you're going to be okay. Now, for the next piece, one more example for today. Again, we're going to use the product rule instead of multiplying the two binomials out. So y prime would be equal to 18x squared minus 1, and then 10 minus 2x, of course. And then we will leave the first function, the 6x cubed minus x, as is. And then we'll take the derivative of the second piece, which will just be -2, because the 10, when you take the derivative, it will give you a 0, and the x, when you take the 2x, when you take the derivative, it will simply become 2. So you have -2 there. And then we're going to multiply this out. Oh, so this is y prime. So this will be 180x squared minus 10 minus 36x cubed plus 2x, and then plus 6x cubed. Oh, sorry, I forgot the 2. Haha. That will be minus 12x cubed plus 2x. And then you'll notice that there are some like terms here. So it will be a good idea to combine those. So we're going to get negative 48x cubed, and then plus 180x squared, plus 4x, and finally minus 10. So organizing the powers of x in descending order. Now, if you're interested, you can also do the question the other way. Include that information here as well. We can multiply the two binomials together. So we'll get 60x cubed minus 10x minus 12x to the 4th power, and then plus 2x squared. Sorry. So this will be the first terms multiplied together to give you 60x cubed The inside terms give you negative 10x. The outside terms give you negative 12x to the fourth power. And finally, the last two terms multiply to give you plus 4x, sorry, plus 2x squared. And now if we take the derivative, you'll notice that we get 180x squared minus 10 minus 48x cubed, and then plus 4x. And if you rearrange terms, you get exactly what we get using the product rule, which is good because the answer should be the same. And that is the product rule. Now, we have only really applied it to powers of x, but it will work for other functions as well. So next day, we're going to go over the quotient rule, but that is it for today. Thank you for listening.